Thanks. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day again, Lord. I thank you for these students and just pray you to help us use this time wisely as we prepare for the test, which is upcoming next week, that you just help us to answer any questions which still remain. And again, Lord, we thank you for your many blessings. You know my prayer, Lord Jesus. Amen. So I had an example for you guys. You may notice we have some visitors. I'm not sure what's going on exactly. I feel like something's happening. I'm not sure what it is. Okay, that's very unnerving. Example. So this, you have a problem in your homework, which is kind of like this, but it's not quite this. And an interesting calculation to do is to calculate e to the I theta, right? So if you look at this and you just understand it to mean the power series, this is 1 plus I theta plus 1/2 I theta squared, 1 over 3 factorial I theta cubed, 1 over 4 factorial I theta to the 4th, plus 1 over 5 factorial I theta to the 5th. Okay, that's enough. But how does I, well, I mean, here I is I squared is minus 1, right? So if I squared is minus 1, what's I cubed? It's I squared times I, right? Which is minus I, right? What's I to the 4th? It's I squared times I squared, which of course is minus 1 times minus 1, which is what? 1. So what's I to the 5th? It's just I again, right? And so the story goes. So we can simplify the power series for e to the I theta, and what we get is 1. This gives me a minus 1/2 theta squared. And then I to the 4th is plus 1, so that's 1 over 4 factorial, theta to the 4th plus dot, 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 right? That's the real part. And then we've got, I, and we can factor out, we got a theta, and then this gives me a minus 1 over 3 factorial theta cubed, and then this piece gives me a plus 1 over 5 factorial theta to the 5th, right? Admittedly, I've organized things with a particular goal in mind, right? And so you can see what's going on. We know this is the cosine of theta, right? And this is nothing more than sine theta. And so here you go. E to the I theta is equal to cosine theta plus I times the sine of theta. There's a derivation of this formula based on power series. If you define the imaginary exponential by a power series, then this is a way to derive Euler's identity, which I pulled from the thin sky earlier this semester, right? We used to calculate trigonometric identities, but here's a proof of it based on series. Any questions about this? I mean, you have a homework problem which is like this, but not quite like this, right? Like your homework problem, it asks you to do something like show cosine of x is 1/2 e to the ix plus e to the minus ix, right? So to do that, you would expand both of these as series, and then when you add them, things will cancel, and all you'll be left with is the cosine series. So it's another way to get at it. Any questions about this? Hey, fun fact. This is bonus. This is not part of the required part of the course, but example 2 if you had something called j and j squared is equal to 1, and you were to calculate e to the j theta in the same way, then you'd get what? So if j squared is equal to 1, that means that we get no signs, right? The pattern's pretty much the same, except there's no signs. Can you recognize what I'm looking at now? Right. Yeah, this is... Someone's really into their costume today, I guess. I don't know. Sinh theta. So yeah, here's the corresponding identity for hyperbolic numbers. E to the j theta is cos theta plus j sinh theta for what it's worth. There it is. I talked to you guys about the Larry-Moe-Curly function the other day, right? Yeah, so if you want, this is also not required, but if you have j cubed equal to 1, then you have e to the j theta is the Curly function plus j times the Moe function plus j squared times the Larry function. There you go. That actually you can also work out. But anyway, now I'm digressing. Of course, this is not calculus 2. This is something else. All right, let me erase the evidence of this before someone finds out I did this in here. Anyway, that's all I got for today. You guys got questions? Go for it. Yes, sir.
Proof on 9.10, number 94.
94. I think I'm going to have to impose my no questions after number 50 rule. Let's see here, 9.10 number, what did you say? 9.10 number what?
Number 94.
94. Oh, actually, this one's not bad. Well, I think I might be able to do this one. Let's see here. We're looking at the sum. Is it n equals 0 to infinity minus 1 to the n, right? Over. Something's going on in here. Something's going on. Not sure what it is, but there's something. Something's happening. All right, minus 1 to the n, 3 to the 1 over 3 to the 2n plus 1. All right. Times 2n plus 1 factorial. So we probably should just scribble over here the things we know, because we need to know them, right? Chief among these is that a over 1 minus r is equal to the sum n equals 0 to infinity, a r to the n. For what? For the absolute value of r being less than 1. This is important. Also important, e to the x. Let me write it as e to the u. E to the u is the sum n equals 0 to infinity of u to the n over n factorial, right? Also important is that cosine of u is the sum, let's say k, I guess we could use n, fine, whatever. N equals 0 to infinity minus 1 to the n, u to the 2n divided by 2n factorial. Sine of u is the sum n equals 0 to infinity minus 1 to the n, u to the 2n plus 1 divided by 2n plus 1 factorial. Am I talking about the right problem? Oh.
It's the irrationality proof is what he was asking about.
Oh. What am I looking at? I like this one more. Yeah, I don't think talking about the irrationality of e-proof in here is probably a good use of time. I can, well, if you ask Nathaniel nicely, he has a picture of how to do it. Maybe he'll share it with you.
Yes, talk to him about it.
Yeah, I mean, basically, what you do is assume that E is rational. Then the limit of the partial sums has to be a rational number, and if you multiply by b, it clears out some fractions, and you're able to show that there's a whole number which is less than 1, which is a contradiction. But it would take us the better part of 30 minutes to really work it out, and it has little to do with anything else we're doing. That's a hard problem. So what was I looking at? 90. Oh, review exercise 94. Since about, I mean, let's just, it's already here, right? So what is this? Can you see what this is? Compare. Yeah, it's a sine. U equals what? Sine of 1/3. Yep. Kind of anticlimactic, huh?
Look at that differential equation problem that I brought.
Ah, yes, yes. Which one's that?
Which one was it? There were several of them. How about 278?
278. Oh, that's one I made up.
Yes.
I should. So let me build up to it. All right, so one of the kind of problems I've asked you is solving a differential equation via series. You have a few homework problems on that. And it's actually really not that complicated. Let me show you. Here's an example. Suppose I want to find first 3 terms in solution to y prime prime, let's say plus x y prime equals to 0. And yeah. Okay, so the way you do this is just to assume the solution is a power series and plug it in. That's it. I mean, that's the sum total of the method, pretty much. So here, I'll look at y equals to, say, a0 plus a1x plus a2x squared plus a3x cubed. That should be enough. What happens when I differentiate 2 times? Well, 1 time. Differentiate 1 time, what do we get? You guys can differentiate term by term, right? And differentiate 2 times. Let's see here. So when you take these and you plug them in into the differential equation, what does that give us? Y prime prime. I probably should keep, what would be the next term here that I didn't write down would be what? Fine. a4x to the 4th, 4a4x cubed. So 12a4x squared would be the next term. All right. So y prime prime gives me 2a2 plus 6a3x plus 12a4x squared. That's my y prime prime term. And then what's x times y prime? Y prime was here, a1 plus 2a2x, and that should do it. I'm only going to keep to x squared, all right? I'm just going to keep to x squared, so I don't need past that. Oh, and that's equal to 0. So I just have to look at that. Okay, so what are the so I got, let's collect things together. I've got 2a2 plus 6a3 plus a1 times x plus 12a4 plus 2a2 x squared so that tells me that, oh, that's weird. All right, guys, I have, I think I've written a singular differential equation here, which is the one kind you can't do this for. Of all the stupid luck, let's see here. Yeah, this is a Frobenius problem. Here, let's fix this. He's no more. All right, get rid of that. Get rid of this. All right. Now, all of a sudden, the problem will be meaningful. Hooray! Sorry about that. I was trying to make something interesting, but I made it too interesting. So that one was so interesting that you're going to have to wait to differential equations to see how to do that one. 2a2 plus a1 plus 6a3 plus 2a2 times x. All right. What was the next term I neglected over here in y prime? 3a3x squared, right? So 12a4 plus 3a3 x squared. So the point is, every one of these coefficients must separately be 0. So what's that give me? I get that 2a2 plus a1 equals to 0. The second thing gives me that 6a3 plus 2a2 is equal to 0. This one gives me that 12a4 plus 3. Where's the a0 going? I don't have any. Oh, right. Duh. Sorry. 3a3. This one's actually still kind of interesting. So what's this say? This says, and this is actually kind of not an entirely typical example. So a2 is minus 1/2 a1 from that equation, right? How about the second equation? What's that tell us? This tells us that a3 is minus 2 over 6 a2. But what's that? That's minus 1/3 a2. But what was a2? We can rewrite a2 in terms of a1, right? See this? I can use it down here. So that's 1/6 a1 is a3. And I can figure out a4. We don't even need it, though. But a4 is minus 1/4 a3, right? Which is minus 1/24 a1. So apparently, all of the coefficients in our solution past 2 and higher are tied to the first coefficient, right? What's the condition on a sub naught? No condition, right? Does that make sense? Well, if you look at this, it does make sense because, so what we're finding is that our solution looks like this. It's a sub naught plus a sub 1. I'll write it out there. A sub 1 times x plus, what's a sub 2? A sub 2 was minus 1/2 a1 x squared, right? Plus 1/6 a1 x cubed. Minus 1/24 a1 x to the 4th, and so forth. So let's clean this up a little bit. We've got a0 plus a1 times x minus 1/2 x squared plus 1/6 x cubed minus 1/24 x to the 4th plus dot, 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 dot. And so there you go. That's actually more than we need. That's the first couple terms in the solution.
That's the power series of, well, that the infinite series is minus x, right?
Hmm?
The power series represented there, right? That infinite sum is e to the minus x.
Oh, yeah. Thank you. Very good. Well, I think it's, well,
The first term split off. The one split off. So not quite.
oh, right. So this would be e to the minus x minus 1, right? Yeah. Kind of funny. It's fairly easy if you go back to the original differential equation to see, does a constant solve the differential equation? If you look at the original problem, does a constant solve it? I mean, look at it. If I look at y prime prime, right, minus y prime equals to 0, clearly y equals to a constant. If you plug that in there, does it work? Yeah. How about exponential? Well, exponential doesn't work, but what if we do e to the minus x? See, then the second derivative is e to the minus x again. And, well, should be a plus, yeah. What did I do? Where is my... Oh. Okay. Thank you. Ay. All right. So this is actually an unfortunately complicated example. I was not trying for this. Let me work one with... This is not the one Nathan wanted to see, actually. It might be helpful. I don't know. Let's look at another one of these. This time, let's find the complete power series solution to a given differential equation. This has lots of interesting calculations, which are worth looking at for you guys. So let's consider find complete solution. Let's look at y prime prime plus 4y equals to 0. So here's what we do. We say y is the sum, n equals 0 to infinity, a sub n, x to the n. Differentiate, what do you get? Differentiate 2 times, what do you get? So how do we, the basic idea here is to guess the solution. This is the technique. We're guessing solution has this form. Now, guessing the solution can be represented as a power series. Is that a terribly restrictive guess? Certainly not. Like, what have we been able to make power series represent? I think pretty much every function that you've dealt with, modulo maybe, I guess we haven't done absolute value, right? I don't expect that the power series can deal with kinks in the graph, right? But smooth functions we definitely got covered for the most part. So it's a reasonable guess to suppose that you can write the solution like that, right? Then what do? We have to plug that in to the differential equation. So plug it in. Y prime prime plus 4y is equal to 0, right? But it's also equal to the sum n equals 2 to infinity of n times n minus 1 times a sub n, excuse me, x to the n minus 2, right, plus 4 times the sum. And what are we going to have to do? You kind of see where we're going here. What are we going to have to do in order to add these series? Yeah, we're going to have to reindex either the first or the second. I suggest we reindex the first one, right? So let's make a substitution. Let's let k equal to n minus 2, right? So then this becomes the sum. K equals to 0 to infinity. So if k is n minus 2, that means n is equal to k plus 2, right? So that gives me k plus 2 times k plus 1 times a sub k plus 2, x to the power k, right? Plus 4 a sub k, because I'm running out of board space here, all times x to the k, right? Does that make sense what I did? I just went ahead and relabeled the second sum just by changing k to n to k. Hope that's okay. Yes? Sorry, it's inevitable. It's going to happen. Yes?
If instead of differentiating the series, if you integrate it, if n is equal to 2 for that series, does that mean that n is equal to 1 once you integrate it?
Well, I don't understand why you're integrating. I'm sorry.
No, I mean, it doesn't have much to do with this, but when you differentiate a series, it goes from n equals 0 to n equals 1 to n equals 2.
Yeah, for this one, we got to be careful. When the power is not just a naked, n, if it's 2n, then we saw that gets us into trouble if we're not careful about it. We got to think through it. Yeah.
I don't understand what we're doing with this.
We are trying to find the solution to the differential equation. The big picture of what's going on is we're supposing that the solution has a power series form.
Okay.
Then all we're doing is we're taking that power series, which we don't know yet. All the a sub 0, a sub 1, a sub 2, a sub 3, these are all unknowns.
Okay.
We're plugging it in to the differential equation, and we're going to see what condition is forced on us to relate the a sub k's to a k plus 2. We're going to get a recursive relation between the coefficients, which is going to allow us to pin it down. Modulo 2, there's always going to be 2 left over. Because when you're solving a second order differential equation, it's like integrating 2 times. There is always like 2 leftover constants in your answer. Easiest case of this is if this one we can solve without. Like this is here's a second order differential equation you can solve in calculus 1. Y prime prime equal to 0. Integrate one time. Y prime equals to C2. Integrate again. Y is equal to C2x plus C1. There you go. That's the general solution to that second order differential equation. This is very precious because we can actually solve it by integrating 2 times. I can't just integrate that 2 times because to integrate it, I have to know the answer. Like if I isolate y prime prime, I got y prime prime equals to minus 4y. Well, that's great. If I integrate one side, in order to actually integrate the other side, I need to know the answer. Kind of a drag. Of course, don't look too hard at that. If you look too hard at that, you're going to guess the solution to this problem already. Don't think about it. You could guess it. That's not the point. I mean, you could guess it, though. You want to try? What function has that? None of you blue-shirted people are allowed to say anything. What function can I differentiate 2 times and give back to minus 4 times the function? Yeah. E to the minus 2x.
E to the I. E to the.
Ooh, you like e to the 2ix? That's not bad. That's not bad. You're right. That would give us 2I squared, e to the 2ix, which would be minus 4. Yeah, you got me there. Now find me a real function, which, but I want a real solution.
Is that allowed in any of the homework?
Well, there is homework which is involving that, so I wouldn't just carte blanche say that that's not allowed in the homework. You know, I mean, in differential equations, though, we're interested in finding real solutions. That's a very good answer. I'm going to leave that there. I'll leave that there. We'll understand that in a bit. Okay, so let me finish this because you got a couple. I asked you guys a couple of problems like this, so I should kind of at least give you an example to work off of, right? All right. So what we have then is we have this has to be 0, right? This has to be 0 for all k. So that gives us a relation. It gives us the fact that k plus 2 times k plus 1 times a sub k plus 2. My k's are hideous. I'm going to switch back to n here in a second. Plus 4 times a sub k is equal to 0. So let me be civilized and rewrite this as saying a n plus 2 must be equal to minus 4 times a sub n divided by n plus 2 times n plus 1. If you don't like the letter you're working with, change letters. So there we go. That's prettier. There you go. That is that's like the fundamental recursive relation. And then what you got to do is just kind of tinker with it. Consider n equals to 0. We get what? We get a2 is minus 4 a sub 0 over what? 2 times 1, right? How about n equals to 1? We get a sub 3 is minus 4 times a sub 1 over 3 times 2, yeah? What happens with n equals to 2? We get a sub 4 is minus 4 times a sub 2 over 4 times 3. But we should always try to break it. Always try to bring it back down to the lowest coefficients which you got sitting around, which in this case are a sub 0 and a sub 1. So you see, I can take this and that and put them together here. This is actually what? Minus 4 squared times a sub 0 over what? 4 times 3 times 2 times 1. Of course, writing the times 1 is optional. I write it to emphasize what's happening. N equals 3. What do you got? We've got a sub 5 is minus 4 a sub 3 over 5 times 4. So I try to carefully generate this formula, and then I just have to study it until I understand the pattern. And for the examples that I think I've asked you, you can understand the pattern with not too much work, I think. Actually, that y prime prime minus 3y prime plus 2y may be unpleasant. Sorry about that one. Yeah, that was probably bad. Okay, so anyway, minus 4 squared, I think, a sub 1 over 5 times 4 times 3 times 2. You guys see the pattern yet? I'm just going to go ahead and point out the pattern. So from this, I can see that if I have a sub 2, let's say j, what is it equal to? Looks like minus 1 to the j times 4 to the j, right? Divided by what? Let me rewrite this. This is minus 1 squared times 4 squared a sub naught, right? And over here, down here, we got 4 factorial, which you could also write as 2 times 2 factorial, you know? Anyway, if you keep going with this, you'll see that the pattern there is 2j, parentheses factorial. And every one of those has a sub naught over here. And on the other hand, if you look at the a sub 2j plus 1 terms, like the n equals to 1 or n equals to 3, you're going to see that you've got a 2j plus 1 factorial downstairs, a minus 1 to the j upstairs. There's a 4 to the j that's happening. 2j plus 1. Maybe I haven't written quite enough for this pattern to be totally obvious, but if you write about another 3 of these, it'll for sure pop out at you. So therefore, this is the kind of, I have to work out this kind of recursive relation if I want to actually find the complete power series, is what I'm getting at, Nathaniel. So in summary, y is equal to a sub 0. The sum, j equals 0 to infinity, minus 1 to the j, 4 to the j, over 2j factorial. This was x to the 2j, right? Plus a sub 1, the sum, j equals 0 to infinity, minus 1 to the j, 4 to the j, over 2j plus 1 factorial, x to the 2j plus 1. And that would be the complete solution, complete power series solution to this differential equation. I hope you see why this is a calculus 2 problem. It's because the calculations are calculus 2, right? I mean, it's nothing more than you plug in a power series, right? And you reindex a sum, and you do algebra. I mean, this is calculus 2, as we're currently experiencing it. This is definitely on the harder end of the problems I might conceivably ask you. I usually chicken out and don't actually put it on the test, but in principle, it could be there. So I put it in the homework for you, because I think working these problems builds your skill set. It's useful. And I also think it demystifies the problem for you when you hit differential equations and are actually asked to do it for real. Okay, or some of you never will take that class. But now that we've done all this, this is actually a more important question, sort of down the middle, right in the heart of the strike zone, so to speak, if you believe in that sort of thing. What are these power series that we found? Yeah. How about this? 4j times x to the 2j is actually equal to what? It's actually equal to 2 to the 2j times x to the 2j, right? Which means by laws of algebra, or algebra, 2x to the 2j. What are these? See, I can, So that's why I was warning you, Prince, don't think too hard because you might guess these.
I don't know if I would guess it.
I think people, I've had students guess these before in the middle, like I'm in the middle of deriving it, and they're like, wouldn't cosine 2x work? I'm like, yes. You've seen through the fact that this is an easy problem that this technique is not really warranted for. And so going back to your guess, Josh, it's not an accident, see, because e to the 2ix has cosine 2x and I times the sine of 2x as the real and imaginary parts of the e to the 2ix function. And when you find a complex solution to a differential equation, you find you find two real solutions, one for the imaginary part, one for the real part. So this actually has both answers in it with the proper interpretation. Your guess is actually both parts of our answer. It's a good guess. It's a twofer. But you got to understand, I am digressing. All right, so enough about this. I should stop doing these. One of the questions in your homework about solving a differential equation is easier than this. Here, let me do one of those. It's much more likely I ask you to find the first three terms on the test. I think that's a much more reasonable calculation. And if I'm careful to ask an interesting one, it's actually a pretty short calculation. The other way to make these less weird is if I give you something like solve y prime prime plus 3y equal to 0, and you know that y of 0 is 1 and y prime of 0 is 2, find the first three terms. That makes it like way easier. See, because then there's no undetermined constants. There's like, well, you got a0 plus a1x plus a2x squared and so forth. But what is the meaning of the 0th? Oh, no. What's the meaning of the 0th and first terms? Go back to Taylor, right? What does Taylor tell us? This is 1, and that's 2. So if I say to find the first three terms, if you understand Taylor's theorem as it interfaces with this problem, you've already got 2/3 credit without doing a bit of work, right? Now to find that a sub 2, I'm going to have to work a little bit. I'm going to have to differentiate 2 times. These are gone. This is becoming 2a2 plus stuff I don't know. And then I've got y prime prime plus 3y. Well, that's 2a2 plus stuff I don't care about plus 3 times y. But what was y? Y was 1 plus 2x plus a2 x squared. And I somehow have made my a2 become a squared, which is interesting, but very, very wrong. And if you look at this being equal to 0, we're already done. See, because the 0th term is a sub 2 plus 3 equals to 0. Therefore, a sub 2 is minus 3/2. And so we find that y is 1 plus 2x minus 3/2 x squared. There you go, first three terms. This example 3 is more on target for what I would actually ask in the test, more likely, right? It's actually a very nice problem because it involves a lot of what we've done. But anyway, let me shut up about that. You guys have other questions? Oh, I'm sorry, I almost forgot. I'm my own worst distraction here. Some of these you don't have to do this way. For example, if I was going to solve x squared dy dx equals to, e to the x squared minus 1. If I was going to solve this, I just caught the moonwalking. I was like, what? I can't do it. This one, like, you might be tempted, now that you've seen this method, to use the method to like plug in an arbitrary coefficient. But this one, what's the power series for this? Well, let me write it out term by term. this would be what? 1 plus x squared plus stuff, right? Minus 1. So the 1's cancel, right? And so what you have is you've got x squared dy dx is equal to, you know, some, we write it this way, n equals 1 to infinity, x squared to the n divided by n factorial. I'm making a u equals x squared substitution, and why am I not starting it at 0? Right, that 0th term canceled out, so I got rid of it. So instead of starting at 0, I start at 1, you know? But then I can divide by x squared, right? So I just, you know, multiply by x to the minus 2. It gets me to this. If I want to solve for y, what do I do? How about integrate, right? So integrate term by term, what do you get? X to the 2n minus 1 over 2n minus 1 times n factorial, right? And then you can add a constant because it's an integration, but there you go. That would be the answer for this question. One of your homework problems, which one was it I'm talking about?
271.
271 is like this. If you look at 271 carefully, everything there has an x in the power series expansion, at least an x in every term. So you can divide that 271 by x, and you can isolate dy dx, and then integrate. So let me just write that down. For problem 271, here's my advice for you guys. Well, first of all, you know, find series for each term, all right? Find the series for each term in that problem. Notice that every one of them has an x in it. So multiply by x to the minus 1, right? Then isolate dy dx equals to stuff. Step 4, integrate to find y. This is how you can do problem 271. It's just like this example I just did. Easier, I think, in some regard. Maybe it's not easier. I don't know. Did I say just find the first 3 terms in that one?
Yes.
The reason I did that,
First 2 terms, actually.
first 2 terms. The reason I did that is because there you've got the product of functions. And to find the power series for the product, it's a drag. But if you just multiply out the first couple terms, that gives you all you need. I shut up. You guys have other questions? Well, you guys are asking me hard questions today.
Can you look at the other one that I asked you this morning? 274? The estimation one?
Is this your question too, Joshua?
I wish I was up there.
The estimation one? What I see, I don't remember. What is the power series for inverse tangent? I mean, we can work it, well, you know, the first few terms.
First 3, I think.
It's right here.
Okay. I think this one we can do alternating. I think this one allows alternating series arguments, so it's not bad. So let's see here. Maybe so 0 to 0.2 of inverse tangent of x cubed plus the sine of x cubed dx. And what did I say? I said this can be approximated by 0.2 to the fourth over 2, apparently. And what's the question? How many decimal places are certain in this approximation? So if you've done your homework, at this point, you've already found the power series for inverse tangent of x cubed in the previous problem. That actually would be restful compared to the other things I've been doing today to find that. Let me take a second. So if I have f of x equals to the inverse tangent of x cubed, differentiate that thing. I feel like I did this the other day, 3x squared. Did you ask me this? Huh, weird. X to the 6th. See, what I'm doing is the derivative with respect to x of inverse tangent of u is what? It's 1 over 1 plus u squared times du dx. But here, u is x cubed. So x cubed squared is x to the 6th, and du dx, well, that's 3x squared, so there you go. Now this is a joy, because this is just geometric series, n equals 0 to infinity, 3x squared minus 1 to the n, x to the 6n. Putting a equals to 3x squared, and r equals to minus x to the 6th. But we should clean that up before we undo the differentiation. N equals 0 to infinity, 3 times minus 1 to the n, x to the 6n plus 2. Now I integrate, and that gets me back to inverse tangent of x cubed equal to, by the way, the value of this at 0 is 0, which means we can neglect the constant. We've done that like 3 billion times in here at this point. For this function, the c works out to 0. N equals 0 to infinity, 3 minus 1 to the n over 6n plus 3, x to the 6n plus 3. So there you go. There is your power series for inverse tangent of x cubed. Let's see here. What's like the first two terms in this? Let's look at it this way. What are the first two terms in this? It's 3x squared minus 3x to the 8th. That's easier to see, isn't it? So when you integrate those, you're going to get x cubed minus 1/3 x to the 9th. Now you can check me on that. Is that what we get? Put n equals 0. I get 3 times 1 divided by 3, 3 over 3, otherwise known as 1, x cubed, yay. Put n equals to 1, 6 plus 3 is 9, minus 1 to the 1 is minus 1, this is a 9, 3 minus 3 over 9 is minus 1/3, yay, okay, great. All of that to tell you, this is really what? X cubed, right? What's the next term in the power series expansion? Minus 1/3 x to the 9th stuff, right? What's the power series expansion for sine of x cubed, though? That's easier. Right? So the first two terms in the sine expansion are also x cubed, but this time minus 1/6. U cubed is x to the 9th here. So these are the first two terms these are the first two terms up to order 9 in the power series approximation to the integrand. Does that make sense what I'm doing so far? I hope. I have no earthly idea why there's a 0.2 to the 4th over 2 on the other side. I'm genuinely mystified by why that number is there at the moment. Seems like it might be a typo. A better version of this question would just be, approximate this integrand using the first term, perhaps the first term in the, anyway, let's keep going. I'll talk about interpretation here in a second. So let's see here. We can combine things. What do we got? We've got integral. Oh, I think I know what it. I think I know what it is. Never mind me. Like I said, I should just keep going. This is 2x cubed, right? And then what do we got at the 9th order? Help me out. Help. Fine, don't help me. Minus 1/2 x to the 9th. I'll remember that. Let's see here. Sorry. Because a half plus a sixth plus a third is a half, right? Yeah. Okay, so then what's this? This is, well, it's 1/2 x to the 4th, right? Minus 1 over 20 x to the 10th plus dot, 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 dot. Now, I love this problem relative to some of your homework because this is alternating, which means we have the alternating series estimation theorem. Woo! The first term in this alternating series is what? It's actually 1/2 0.2 to the 4th. Aha, the mysterious 0.2 to the 4th over 2 has appeared. Apparently I did know what I was doing when I made up this problem. Hooray. And then, what's next is minus 1 over 20, 0.2 to the 10th power, and then plus stuff I don't care about. So when I write that integral is equal to 0.2 to the 4th over 2, right? What am I neglecting? Everything in this alternating series past the first term. But what's the magnitude of the error bounded by? The absolute value of the second term. Right, so there you're looking at it right there. That's how accurate we know the answer to. Not too shabby, really. What's that?
Is it always just going to be the absolute value of the second term?
It depends on how far we go. If I took the first two terms, then I'd have to calculate a third thing to find the error. You know? It's always the next thing you haven't used for an alternating series. For a series which is not alternating, the next thing you don't use is still a good back-of-the-envelope estimate for what the error is and what you already have. But there are counterexamples, and we have to fall back on Lagrange's theorem to be careful for the remainder. Josh, you must have a question. Does that help with this one?
Yes.
I hope. I mean, that's the solution. Pretty much the solution to the problem I seem to have. And I think I've inadvertently worked the problem before it, too. Dang it. I should just end class early to stop myself from doing any more of this.
Well, it's the problem I told you I would ask you.
Oh, okay.
9.10 number 14.
9.10 number. So I was warned, is what you're telling me. Let's see here. 9.10 number 14. Ah. You're trying to break my brain today. All right. So here we're supposed to prove that the Maclaurin series for the function converges to the function for all x, and we're looking at e to the minus 2x. All right. So this problem asks us to show that e to the minus 2x is analytic